All right. Welcome back to our fourth installment in our unit on functions, where we'll be looking more specifically at an idea known as the rate of change. It's definitely an old idea, or it's a new word based on an old idea. But we're going to be learning that given a graph of a function to estimate or calculate the average rate of change over a specified interval. So I can understand that the average rate of change describes how fast the output of a function changes for every unit of change in the input. I'll know I've got it when given a graph of a function, I can estimate or calculate the average rate of change between 2 points. All right, so the average rate of change of the function y equals f of x between x equals a and x equals b is the change. It's a math type. Change in y divided by our change in x, which should look pretty familiar, or at least jog your memory. Remember, if we wanted to determine the change in y, right, that would be the function value at one point, so point B, subtracted by the function value at point A, divided by the change in x, so that would just be the distance between B and A. That expression should look extremely familiar. So the average rate of change is the slope of the secant line between x equals a and x equals b on the graph of f. That is the line that passes through the following points: a, f of a, right? So that's point 1, and b, f of b, that would be point 2. And if we kind of take a look at our corresponding graph here, right, this particular point will represent x value of a and a y value of f of a. This point up top would be an x value of b and then y value of f of b. And hopefully you've come to realize that this is nothing more than slope, but between two arbitrary points on a curve, rather than kind of a straight line. In the expression for the average rate of change, the numerator f of b minus f of a is the net change in the value of f between x equals a and x equals b. So with that being said, I'd like for you to take a moment here to, with this function, determine the average rate of change between x equals 2 and x equals 4. In the event that we have an object dropped from a high cliff or tall building, the distance it has fallen after t seconds is given by the function d of t equals 16t squared. Find its average speed over the following intervals. If we wanted to determine what the average speed was between 1 and 5 seconds, we would first need to determine what are the outputs. So at 1, right, at a time interval of 1 second, the distance that the object has fallen is 16, we'll go with meters here, and vice versa at 5. We would replicate that process, substituting those values into the variable t in the equation. 5 squared is 25, and 25 times 16, I want to say, wow, it's pretty big, 250 and another 150, so 400. Don't quote me. And if I want to calculate its average speed, I would have to take d of 5, difference between those two outputs, divided by the difference of their inputs. Should be 384 divided by 4, which will give us an approximate value. Just double check that 25 times 16 was 400. That gives us the value of 96. So over those, like I said, meters per second. Oops, per second. So replicate that process, but now instead of define numerical values, we're looking at this more abstractly with time being some arbitrary point A, and obviously A plus H representing some arbitrary time later. The reason why I'm asking you to do that is because at some point you'll probably find yourself in calculus, and the average rate of change that you're going to calculate above is known as the difference quotient. In the world of calculus, you'll use difference quotients to calculate instantaneous rates of change. An example of that would be the speed shown on the speedometer of your car. It changes from one instant to the next as your car's speed changes. Recall that a secant line measures the slope between two, that shouldn't be lines, but points. If you forgot, go back to slide 2 where we spoke about this. Function of the form f of x equals mx plus b is a linear function. How would you describe the rate of change for a linear function? So if you've watched this video, I've already used the particular word, but I'll leave this up to you and your peers to kind of define. So in this instance, once again, we're kind of going to replicate the process that we just did with the falling object, finding the average rate of change between these particular points. And you should come to notice something, especially for this type of function. In essence, the average rate of change of a linear function between any two points is the constant m, which is the function, which is a linear function's slope. So connecting this idea of rate of change and slope, okay, they essentially are describing the same concept, but two different phrases. So in here, we have a set of data regarding an outdoor temperature. First, you'll calculate or draw a visual representation of the temperature, and our time t is measured in hours since midnight. So at this point, 0, it is currently midnight. So at 1, it would be 1 a.m., so on and so forth. That's a huge hint because notice our table value starts at 8 a.m. In this instance, you are tasked with determining what the average rate of change of temperature is for the following times: 8 and 9 a.m., 1 and 3 p.m., 4 and 7 p.m. And at that point, we'll pause before we're picking up together tomorrow in the enhancement opportunities.